Hello all! Today we're tackling the problem of electric field due to a ring charge. Here we have a ring charge with total charge Q and radius R. And we're trying to calculate the electric field along the center axis of this ring charge at a distance x, let's say at this point P. Alright, let's get started, you guys. First and foremost, we have to define a coordinate system in order to be able to show our vectors, vector components, and define our integral limits. So let's put a coordinate system right at the center of this ring, such that this ring is on the YZ plane of our coordinate system and the center axis is our x-axis. So we have a number of steps we can follow to solve a problem like this one. Well, the whole goal here is to use the electric field of a point charge in order to reach a conclusion about the electric field of a charge distribution. For that, on our charge distribution, we define a small charge dq and then write a dE, a small electric field of that charge distribution. And then use integration to solve for the total electric field at point P. So hence, we start out by picking a random charge on our charge distribution. We define it in terms of the charge distribution, line, surface, volume, whatever it may require. Then we rewrite our dE, and dE will have this expression R. We have to define that, and then we define our x, y, z components of our vectors, define our limits, which will show us where the charge is on our coordinate system, and solve the integral and reach a conclusion. So here is a summary of the steps, and we can have it as a guide while we're solving the problem. So let's get started. Let's start out by picking a random charge on our charge distribution. Let's pick this dq. And we can define dq using this formula for a line charge distribution, lambda. Since this ring is a line distribution, what is lambda? We're not given a lambda in the question. It's the total charge Q distributed across the length of the circle 2 pi r. So rewriting dq is Q over 2 pi r dl. We have to redefine this length, the small length of this dq. For that, we're going to need to define an angle. So let's define an angle on the plane of the ring, angle phi, starting from the y-axis. Well, a small arc length is radius of the curvature r here times a small angle on that plane. We're going to call it d phi since we define this angle phi. So rewriting dq, we have defined it, and our first step is done. Q over 2 pi r d phi. And as you can see, r's will cancel off. We're going to be left with Q over 2 pi d phi. Let's write it up here. All right, we have dq defined. Beautiful. So now we're going to show the dE vector created by this dq. And it's going to be along the line that joins dq to point P, and it's going to be pointing away from the charge since it's positive. So there's our vector. So we're going to use the definition of a point charge's electric field. So this small dE is k dq over r squared. Beautiful. Well, now we have to define the r in the expression. But what is that r? Well, it's the distance between dq and P, between the point charge and the point of interest. So here is our r. Well, we're going to use this triangle to define r. As you can see, this x-axis is perpendicular to the yz plane, hence it's perpendicular to the plane of the ring. So this triangle formed along between this x-axis and the line joining dq to the center of the ring and r here we have this triangle. It's a right angular triangle, and we can use that triangle to define r, because it's the hypotenuse in a right angular triangle. So it's going to be sum of squares of the two sides of the triangle. One is x and the other one is this radius r. Here we go. So now we can rewrite our dE, plugging everything in. We have q over 2 pi d phi times k, x squared plus r squared, because it's r's square at the denominator here. Beautiful. So now we have a dE defined. We can put this 2 pi down there. All right. So here we have the dE rewritten. Now our next step is to define the components of this electric field vector, dE. So let's define this angle theta, and the same angle theta is going to be in this triangle that we defined earlier. All right, so we can use this triangle to write a sine and a cosine expression for theta. The electric field will have a component along the x-axis, dEx. And I'm going to define this component of the electric field, which is a reflection of the vector on the yz plane, and call it dEyz. And yz will have the exact same direction as this vector right here. So this is a reflection of dEyz on the plane of the ring. All right. So I can use sine and cosine of theta to define these vectors. dEx being dE times cosine of this angle theta, and dEyz being dE times sine of this angle theta. All right. Now, at this step, you guys, depending on what kind of a charge distribution you have, you can try to find a dq, another dq, probably a symmetrical dq, however you define symmetry though. But we will define a dq prime here on towards, like across the ring towards the other side, dq prime, and then write the dE prime created by this dq prime. What are we trying to do? Well, we're trying to find another dq to cancel off one of these components if possible. All right, so this dE prime will have a reflection on the yz plane, a yz component, dE prime yz, and this dE prime yz will be pointing towards this direction along this line, and this was dEyz. Okay, direction of dEyz. This is the direction of dE prime yz. They will have the same x component along this x-axis towards positive x direction. And if you guys can see this, imagine this in 3 dimensions, this dEyz component of the vector dE is opposite to dE prime yz. They will have opposite directions, and they will have the exact same r, same dq, so they will have the same magnitude but opposite directions. So the total yz component of this vector dEyz will be 0. They will cancel each other off. So for every dq, I can find a dq prime to cancel off its yz component. Hence, the total yz component will be 0. All right? So our total vector is going to be along the x direction. So all we need to define now is define a cosine theta and rewrite dEx. All right, wonderful. So I'm looking at this triangle. In this triangle, cosine of angle theta is the neighboring side, x, divided by the hypotenuse, which is r. So it's x squared plus r squared square root, or to the power 1/2. So that is our cosine. So let's rewrite a dEx then. So we have kq over 2 pi x squared plus r squared. And from the cosine expression, I'm going to have x over x squared plus r squared to the power 1/2. So combining the two, I'm going to have x squared plus r squared to the power 1 plus 1/2, which is 3 over 2. All right. And then I have an x up here and a d phi. Wonderful. We're almost there. So let's have the x up here. So now all we need to do is to put this in an integral, define limits properly, and we're done with the problem. How do we define these limits? Where our integral is over the angle phi. So now I have to go to my coordinate system and see what this phi corresponds to when I'm scanning my line charge. So here is my line charge. To be able to cover all of this line charge in my limits expression, I have to start phi from here. This is my phi equals 0 point, going all the way phi equals pi half, going all the way down here phi equals pi, 3 pi over 2, and back to phi equals 2 pi. So my limits will scan the whole circle from 0 to 2 pi. All right, so I can do the integration and be done with the problem. Just scratch that. So we'll have an x component of our vector, and everything in here is going to be constant. K, Q, X, 2 pi. None of these depend on the angle phi. So they're all constants for my integral, and all I have left in the integral is a d phi. And this integral of d phi is just phi from 0 to 2 pi, which is 2 pi minus 0 when you put the limits in, leading to an angle of 2 pi. So this here is 2 pi. We have an EX that is KQX, all right, over, well, this is 2 pi. We have 2 pi in the denominator, so they cancel each other off. We have x squared plus r squared in the denominator to the power 3/2. And this is our EX. We have an electric field that is pointing towards the positive x direction, and its magnitude is kqx over x squared plus r squared to the power 3/2, and hence we have a result. As you can see, as x goes to 0, we're calculating the electric field at the center of the ring. When x equals 0, electric field at the center of the ring is also 0. Electric field at point O is also 0. All right, so now we've solved this problem, and I will see you in the next problem.